Good afternoon, everyone. Let's give a couple of minutes for everybody to settle down. So this is the last official presentation of PGConf India 2020, right? I always forget to get onto the stage, stage fright. So yeah, I mean, this is the last official presentation, and but there's more. We have lightning talks happening after this. So thanks for the response. It's much better than yesterday. So if anybody is still interested, please submit your talks. Okay, so let's get started. My talk is towards full ACID distributed transactions with foreign data wrappers. The title says towards. That should tell you that it's work in progress. It hasn't made its way into the core, but the idea here is to give you a glimpse of the efforts that are happening on that front, right? In yesterday's keynote, we heard, right, distributed PostgreSQL is a game changer, right? And a lot of efforts are happening around that, and I would say this effort is the one that is happening from inside core Postgres, right? There are other external efforts that are happening. So let's see what we're trying to do here in core Postgres. Standard stuff, who am I? So I've been fortunate to work on the PostgreSQL code since 2006. Somebody was asking me, which is your key area that you've worked on, and I was wondering, I think I have worked across the breadth of the code, which I think is a good thing. I'm a jack of all, master of none, right? So I've been a part of few startups. I've done one startup with Jim, who is with us, and I tried some stuff on my own. But currently, I'm a full-time co-organizer of PGConf India and a full-time consultant at 2ndQuadrant. So I'm sure we have had a lot of talks, and I don't need to discuss in depth about this, but what is FDW, right? FDW stands for Foreign Data Wrapper, and it's the implementation of the SQL MED standard, the SQL standard for MED, which is management of external data, right? So Postgres has local data, and the standards specify how you can access external data from inside Postgres, right? So Postgres has implemented that, and we call that as FDW, right? As with Postgres, things Postgres, everything is extensible. So even this is a pluggable architecture, right? So what that means is you could implement a foreign data wrapper for any thing that can provide a transactional interface, right? So you could have your local PostgreSQL configured to connect to a remote MySQL server or a Postgres server or an Oracle server. It could connect to a file if that file exposes the APIs of a foreign data wrapper. Or I remember there was a black hole foreign data wrapper. You put anything into it, it just disappears, right? You can never select back from it, So it's implementation dependent, right? So you can come up with your own FDWs. I think there are FDWs for Kafka or things like that. More and more people are coming up with these kind of wrappers nowadays. So what we do in Postgres is we have the concept of a foreign table, right? Vis-a-vis the local traditional tables that we have in Postgres. So there are standard tables, and then there are foreign tables. And as the name suggests, the foreign tables are present remotely, right? And whenever a query happens, comes in from the client, you only have the metadata for that foreign table present locally in Postgres, and Postgres then uses that metadata to convert that query onto the appropriate remote foreign data foreign server, right? So as you can see here, there is a users table, which is a foreign table. The client made a query to Postgres. It need not even know whether it's a local table or a remote table, right? PostgreSQL will convert that query into an underlying query which can be understood by the remote server and fetch the data from that remote side. So, in general, the foreign servers could be a mix of different databases, but here for simplicity, we are just mentioning the remote servers as PostgreSQL servers as well. So the first implementation that we had of foreign data wrappers was to support select queries, right? So you could make queries against remote select queries, and we optimized that operation to try to push down as much as that part of that query as we can to the remote side, right? So for example, if you think of it, a naive implementation is, just implement select star from table, right? And get all the results locally, and then do all the post-processing, right? But let's say you're doing select from table where with a where clause, and only 10 rows from the remote side meet that where clause, right? And in this case, if you had millions of rows on the other side, getting those locally and then applying the where clause locally is very, very expensive, right? So most of the operations that we want to carry out on foreign tables, we want to push them down to the other side. Join is again an example of a very expensive query, right? You have two tables, you have a join clause, and you're getting complex data out of that, right? Again, in this case, if one table is local and the other is remote, you cannot do much other than pushing down the predicates for the remote table. But what if both the tables are remote tables, right? So in that case, it makes sense to push that entire join query to the other side. So PostgreSQL has done all these kind of optimizations wherever possible. We then added a writable foreign table support. What does writable mean? You can do inserts, updates, and deletes on the remote objects in the remote servers. So that was added in 9.3, and we have continued to make enhancements in the next releases as well. So things were easy with reads, right? When you talk about writes, that is where transactions and processing and issues in transactions come into the picture, right? Now, even on a local PostgreSQL instance, if you want to do transactions, so basically transaction is a unit of work, right? You have some logic that you want to do acidly, right? Atomicity, consistency, isolation, durability, right? But you also want concurrency, right? I mean, we talk about concurrent database access, right? I mean, nobody's happy with just having one client connecting and then waiting for it to complete and move on, so forth, right? So concurrent transactions can cause anomalies, and these have been explained in the PostgreSQL docs as well. I just picked it up from there. So the anomalies are, you can have a dirty read, right? One transaction is doing, let's say, an update on one row. Another transaction concurrently is doing an update on the same row, right? The first transaction made a change to the row values, and the other transaction then again tried to do a change to that same row values. So in this case, if you allow dirty reads, the second update might be able to see the updates from the first one, right? So I don't want to confuse regarding all of this, but then the next is non-repeatable read, right? You did a select count star from table in your transaction. Let's say you got 100 rows there was a concurrent transaction which deleted 10 rows, right? Now in the same transaction, you do select count star from table, right? Now here you'll get 90 rows if the concurrent transaction had committed, right? So it's a non-repeatable read. But some applications expect repeatable read behavior, right? That, I got some value when I started a transaction, and when I read it again, I should get the same consistent view, right? So that is what repeatable read is. There's a phantom read as well. And you have a where clause, and you got a result set. Let's say you got 10 rows, right? Maybe, for example, we as organizers were trying to order T-shirts for our female attendees, right? And we said, give us the total number of attendees with gender equal to female, right? And then concurrent operations happened, more registrations happened, things like that happened, and then again after that, when we reran that same query with the same where clause, we got a different set of output, right? So this is called as phantom read. The most strictest thing that we can support is called as serialization. So here we assume that transactions, if they happen concurrently or in serial order, in any order, they should have the same effect, right? So if updates are happening on different tables or rows, it's fine, but if it's happening on the same row, one update happening later or earlier, the results will be different, right? So this is a serialization anomaly. So just wanted to put that into your heads before moving on. So for this C and I in ACID, PostgreSQL uses MVCC with snapshot isolation. Pawan did a talk on MVCC, right? So basically, the idea is readers don't block each other, and writers don't. Readers and writers don't block each other, right? So that happens because you can create your own version of the row when you make a modification to it. So the readers can continue to see the old version, and the writer can work with its own scratch pad, right? And snapshot isolation. A snapshot is a view of the database at any given point in time, right? So the database is in constant flux, right? You are doing millions of concurrent operations on it all the time, and it's with the use of a snapshot that you can view a consistent view of the database at that given point in time, right? So using that snapshot, PostgreSQL will tell you whether a row is visible to that transaction or not, right? So a snapshot in Postgres looks like this, right? The example. So here it says 10:20, a comma separated list of IDs. So all of these are transaction IDs. Every transaction, as Pawan mentioned, gets a 32-bit ID, transaction ID. And what the snapshot says here is that 10 is the xmin, 20 is the xmax, and the comma separated list is the list of concurrent transactions. Xmin of value 10 means that all transactions with IDs below 10, we know the status of them, whether they are committed or aborted. 20 means all transactions with XID 20 and above are invisible to this transaction, right? And then you have a list of concurrent active transactions that are there in the system. And it's using, via the use of these snapshots that we can come up with the visibility for each transaction uniquely and consistently, right? So again, lifted from our very good PostgreSQL documentation. The earlier slide talked about things like non-repeatable read, phantom read, serialization. Dirty read I have skipped, because PostgreSQL allows you to run your transaction in various transaction isolation level, right? So the first column you see are the transaction isolation levels that are supported in Postgres. Read committed is not supported as such. It is implemented as read committed, right? We support repeatable read and serializable. And as you go down, the stricter the rules become in terms of visibility and more the chance of conflicts coming up due to concurrent access, right? So by default, Postgres runs in the read committed isolation level. So if you just do a begin, that transaction block is using read committed, right? And in that, you can get non-repeatable reads, right? And so on and so forth. So, even on a standalone PostgreSQL instance, you have this challenge with transactions and visibility and how which mode to use and so on and so forth. So things become more exciting and crazier with FDWs, right? So now, because you support writes with FDWs, you have to start thinking about transactions which involve multiple nodes now, right? It's possible that you are updating data locally on remote server 1, remote server 2, and so on and so forth, right? So the FDW that we have in Postgres, it is responsible for implicit transaction management on the remote nodes. As I said, the client might not even be aware that it is talking to remote tables, and it is the job of the FDW to do the actual transaction management when data is being modified on remote locations. So the plugin exposes APIs and implements the standard begin transaction on a remote node, commit on a remote node, rollback, and even save points, right? So a save point is a point in a transaction where you save the transaction state so that later if you do any activity which causes errors, you can choose to go back to that saved transaction state at that save point, right? And there are callbacks which have been implemented in the PostgreSQL source base. Whenever you want to conclude a foreign transaction, you'll call this transact callback, and then commit locally based on the outcome of that call. So here are some details of how currently we do transaction management with Postgres FDW, right? So we don't create hundreds of connections to all your remote servers at one go, right? It's only when you access a specific remote table from a specific remote server, that is when you would start a foreign transaction for the first time on that remote node. In terms of the isolation levels, if your local transaction is using serializable, it will also use serializable on the remote servers. This means that your remote server should be capable enough to support these isolation levels as well, right? But if almost all modern transaction databases support this, Oracle, MySQL, so all your practical use cases should be covered. Even if you use read committed locally in your transaction, and if it is touching a remote transaction, it uses repeatable read. Now, you might ask why it's doing that. We use repeatable read because we want to ensure that multiple scans within a transaction on your local node sees the same consistent view on the other side, right? So now let's look at the problems that might come in this distributed environment, right, of FDW and supporting writable transactions, right? So I guess let me just use a picture. So this is how transactions happen, right? a client connects to the instance, does some work, and says commit. When Postgres is processing that commit, it realizes that remote servers are involved. So it will also send a commit one by one to the remote servers. So it sends a commit to remote 1 server. The remote 1 server does its job, returns success. Then on the receipt of that success, it will go to the remote server 2, send a commit request, and get the response. If all of the remote servers say okay, then Postgres, the local server, will return okay. The coord here stands for coordinator nodes, but you can call it a coordinator or the originating node, right? So wherever the transaction originates, that's called as the coordinator node. When things are working fine, this will work fine in like 98% of your cases, when everything is up, everything is hunky-dory. But what happens when this happens, right? So client said commit, we were successful in committing on remote 1 server, but before the remote 2 server could commit, there were issues. And it could be anything, right? Network issues, or subnet partition, or the machine panicking, running out of storage space, whatever, right? There are multiple reasons, but the commit can fail, right? So in this case, it can return an error to the client, but now the question is, how do you recover, right? Here we have a situation where the local node has not committed. There is a remote node 1 which is committed, and remote 2 node doesn't have an idea of it, right? So your setup is inconsistent, right? And that is a problem which we want to avoid when we are dealing with foreign data wrappers, right? So the standard solution, if you look at database fundamental books and all, right? The standard solution for ensuring atomic commit in a distributed setup is the use of two-phase commit. So this 2PC, two-phase commit, consists of two phases. The first phase is what is called as the prepare commit phase, and the second phase is the commit prepared phase, right? So in essence, what happens is, instead of sending a commit immediately to the remote side, what we ask them is, are you guys prepare yourself for this commit, right? And then it gets a response from all the nodes saying, okay, we are prepared. And only when all of them respond positively do we tell them to commit the prepared transaction. If any of them says it has issues, then you abort the transaction on all the others, right? So, so this was proposed, and it was acceptable to the community as a viable solution to implement distributed transactions with FDW. And as I said, at the disclaimer, this is work in progress. This has not yet made into the code base, and it's been a while, that efforts have happened here. And the patches that are there in the community, they expose new APIs. So, an API to get a ID for that prepare operation, an API to ask a transaction to a foreign server to prepare that transaction, an API to commit remotely, and so on and so forth. And the proposal was, we'll do the following steps. We'll prepare our foreign transactions. We'll get their responses. If they're all okay, we'll commit locally. Once we've committed locally, we'll issue a commit prepared to all the foreign servers, right? So, yeah. So I knew you were going to ask that question. So yeah. Compared with the earlier diagram, which was pretty simple, but now we have the client still sends a commit, but the FDW will convert that into an implicit two-phase commit, right? PostgreSQL also supports an explicit two-phase commit. an application can choose to say prepare transaction and then the ID and then commit transaction, right? So in terms of implementation, this prepare is basically, it does the same activity that a local transaction would do, but it does, it saves all the data and everything else, but it does not make the effects of those transactions visible to the database, right? So the transaction is in prepared state, and until and unless you tell it to actually do a commit, it will remain in that prepared state, right? And only when you say a commit prepared, will the effects of that transaction become visible to everybody else, right? So now what happens is the client commits, connects to the coordinator, issues a commit, it sends a prepare and gets the response from all the nodes. Only when all the nodes say okay, does it do a commit on the remote sides. So if the question was, remote 1 said prepare is okay, but remote 2 could not be contacted for some reason, or it could not prepare for some reason, right? In that case, instead of sending a commit to the remote side, it will send a abort prepared to the other side, right? So it will have to do a cleanup if a transaction, a distributed transaction fails, right? Yeah. So the next scenario is prepare was okay, and commit prepared was okayed by remote server 1, but now you again couldn't reach remote server 2, right? Now in this case, you need what is called as a foreign transaction resolver, and the job of that resolver is to resolve these kind of transactions, right? So let's say remote 2 node was rebooted or crashed, right? When it comes back, the resolver on the coordinator will query it and say, what is the status of this prepared transaction on you, right? As I said, every prepared transaction gets an ID by which you can uniquely identify that prepared transaction. So when remote server 2 comes back, we can inquire and say, tell me the status of this. Is it still prepared or has it committed, right? If it is committed, you don't need to do anything. If it is in a prepared state, you can now ask it to commit that transaction, right? So the point of doing these multiple phases, the first phase is to make all the servers ready, and ready in the sense it is persistently ready. So even if it crashes or comes back, it will still remember that information. And then you can tell it to either abort that prepared transaction or roll back the prepared transaction, right? Yeah, that's what I said, right? Whenever it is, the next time it is reachable, you will query the status of the transaction, and it will tell you it has. Sorry? So look at the steps, right? The step 2 is commit locally, and only then do we send the commit prepared to the other side, right? Prepare is almost commit state, right? So you've committed locally, you prepared all the remote transactions. So when the remote transaction, which was not reachable earlier, when it comes back, you say commit on yourself. Yeah, obviously, but this is a distributed setup, right? So you can write a aggressive foreign transaction resolver, which is like, the moment it comes up, it immediately asks it to commit the prepared transaction. So yeah, now you can see, right? This takes care of all your commit-related issues, right? And That's a problem, right? I mean, and if you're relying on distributed transactions for your work, then you should have ample monitoring and ample, reports to tell you that, yeah, so we are doing that, bringing that protection by doing the prepare, right? And once it is prepared, it's up to you to decide whether you want to commit that to make the effects visible or abort that, right? Yeah, exactly. Yeah. Yeah, I mean, so yeah, I mean, that is the problem, of distributed transactions. You have these to deal with multiple nodes, and uh, depending on at what point the prepared activity happens, currently it happens one by one, right? Even if you do it parallelly, there is, it's not going to happen instantaneously at all the nodes at the same time, right? So yeah. No, I mean, what if what if steps 3 fails? What if the local commit crashes? What do you do then? Right. So no, right. I mean, if stage step 2 fails locally, then when the machine restarts, it will send an abort prepared to the other side, right? Because it will see that locally that transaction has not been able to commit. And when it comes back, the resolver on that node will, instead of sending a commit prepared, it will send an abort to remote 1 and remote 2, right? So we have to ensure atomic commit across the nodes. So you cannot change the sequencing. Yeah. But have you already committed on the remote 1? So how can you roll it back? It's already been committed, right? Yeah, see, there are no guarantees, external that, I mean, when you use 2PC, you're using this multi-step commit process, and if it is prepared on all the nodes successfully, if it has been committed locally, right, then you can commit on all the other remote nodes. If it has been committed locally and it has been committed on one node, then you should commit on all the nodes which come back, right? Any other scenario, you can have the flexibility to do an abort on the nodes. That is what the foreign transaction resolver does. Yes. That is what it has to do, right? So yeah, I mean, things are complicated, right, when you're dealing with distributed setups. Yeah. Yeah, obviously, this has to persist, right, and it has to survive crashes and restarts and all of that, right? So all of this information about foreign transactions is recorded in wall records, right? So when the server comes back, it has the information as to what transaction was ongoing, in what state it can be, and that's how it can get the ID of the prepared transaction, and that's how, using that, it can query that remote side saying, what is the status of this prepared transaction on you? That's the idea of prepare, right? Make the system prepared for the commit, and once all of them are prepared, you can commit the transaction even if there are issues, and even if one node takes time to come back, and so on and so forth, right? So yeah, as I said, all of this information is stored persistently, so that, in case of restarts, you can basically redo the standard PostgreSQL way of dealing with restarts. And as I said, the transaction resolver will query the state of the transactions and decide what needs to be done. So 2PC solves the atomic commit problem. It is mentioned here, the logic, right? I mean, as I said, if you're prepared everywhere, if you've committed locally, then you can commit everywhere, right? If you prepared everywhere, you could not commit locally. When you restart, you should do an abort everywhere. So that was about atomic commit, right? Solved, done, dusted, easy, right? Let's move on to the other problems. The other problem is about atomic visibility, right? And as I said, the client is could be totally unaware that it is dealing with foreign tables, and it expects the same behavior that it expects from a local standalone Postgres server, right? But unfortunately, if you're dealing with multiple nodes, then there are anomalies again, right? So let's see an example of an inconsistent read, right? So here you have two clients, client A and B, connecting to your local instance. There's a remote table involved, and that remote table has 100 rows, right? You will, so by default, Postgres enforces read committed, right? Isolation level locally. But as I earlier mentioned, when dealing with FDW, you use repeatable read on the remote side. So now local client begins a transaction, and it does a select count star from remote table, right? As I said, it had 100 rows. So the answer that we get is 100, right? Now, concurrently, local client B starts up and deletes 10 rows from the remote table, right? Now, because that client is using read committed, he would expect that at the step number 6, when it reruns the count star, it expects that it should see 90, right? But it will see 100 again, right? And that is because since we want a consistent scan from the remote side, we start the transaction on the remote side with repeatable read mode isolation. So this is an inconsistent read example, right? Let's move on to another example where you have, so even with one node, you can get inconsistent read, right? Which is an issue. The second example is with multiple remote nodes, the common scenario which you might face, right? So again, you have two clients, and there are two tables from remote server 1 and 2, and each has 100 rows. So let's say you say, okay, I understand, read committed doesn't work, so let me use read repeatable on my transaction, right? Now it will start a local read repeatable read transaction, and it does a select count star from table on remote 1 server, right? So that will create a repeatable read connection transaction on the remote server 1. Now, simultaneously, concurrently, local client B again starts with repeatable read, and it does a delete from server 2, right? Where ID less than 10. Now, on a standalone Postgres server, if you run a count star on table 2, you would still expect 100 as the count of the rows. But here, at step number 6, when you do select count star from table on remote 2 server, as I said, only when you connect, only then you start a transaction. And even though it is in repeatable read mode, because it was started much later on server 2, you will see the effect of the delete inside your first transaction, right? So it's very difficult to provide guarantees when you are dealing with multiple nodes. So what is the solution for this, right? I mean, earlier, I showed you the scenario, and then I said the solution was 2PC for atomic commit. Let's see if there's any solution for atomic visibility across the multiple nodes. One way is to provide a global consistent snapshots, right? And these snapshots could actually be regular PostgreSQL snapshots, right? So if you remember the snapshot that I showed you, 10:20, and the list of active IP XIDs, you could use a similar snapshots which give you a global list across all the nodes in the system, right? Or you could use like a global commit sequence number. There are some implementations which use that, or even a timestamp, right? So we'll look at some of the solutions out there and what kind of approaches they use. Postgres Excel, it's a OLTP multi-master kind of a solution, right? And it has what is called as a GTM, Global Transaction Manager, which is a dedicated node. And all the nodes, before they start a transaction, they connect to the GTM and ask for a snapshot. The GTM knows what all transactions are active across all the nodes and returns a global snapshot comprising of all those values, right? Similarly, there's a Google product called as Percolator, and it has an oracle. I mean, not the database oracle, but an oracle is something which tells you wise stuff, right? So timestamp oracle, which can produce timestamps in strictly increasing order, unique. And using that timestamp, read and write operations can happen. But you can, somebody will quickly say, right? Sir will say, but this is a single point of failure, right? And what if the GTM goes away? Your system will come to a complete standstill, right? So Excel tried to solve that by using standby for GTM standby, right? And then if the GTM went away, you could promote the GTM standby to become your new main GTM, right? So different products try to solve that solution in a different fashion, right? But the problem with this is not just a single point of failure, but even if you want to scale a lot, if you have a lot of connections coming in, then even that GTM is not able to scale, because it's one entity and everybody's connecting to it saying, give me snapshot, right? So even it can also become a performance bottleneck. So there's a recent paper by Microsoft. It is about clock SI, which is like, snapshot SLI isolation using loosely synchronized clocks, right? So here the idea is to use the time as the commit sequence number, right? And everybody must have heard of NTP, right? Network Time Protocol. So you could have all your nodes synchronized using NTP so that everybody sees the same, roughly, there's going to be some clock skew, but overall it should be pretty good. And using that, roughly, obviously it's a very complicated paper, but roughly a node can use its local time as a snapshot, right? And using that, it can ask the other nodes to return data. And the semantics that we allow is that if you get a snapshot which is ahead of the local time, you simply wait for that time before you return data. So in this case, the visibility of each row is based on the commit timestamp of the transaction which added that row or modified that row, right? As long as your commit timestamp data is less than the SI snapshot, clock SI snapshot, it should be visible to that query, right? So the good thing about this is, it is like, loosely synchronized, right? There is no GTM to go to, or there is no complicated, so it performs better, it scales better as well, right? So for FDW as well, we are recommending the use of something like this, right? A timestamp-based MVCC check, which will, just look at the commit timestamp. So PostgreSQL already supports commit timestamp, right? So when you enable that, every commit when happens, you store the commit's timestamp with it, right? And then using that, you should be able to answer your visibility queries, right? So yeah, this has been proposed, but this could be actually useful in warehousing type of queries, right? Where you don't, we are okay with some amount of stale data, right? Some things like that. A good implementation could actually be used as a serious snapshot implementation as well, right? So yeah, I did not end by saying that, atomic visibility problem has been solved, right? We have just mentioned that, this is a very promising way to look at visibility of data, right? So yeah, as I said, all of this is in work is in flux right now. It's complicated, so that's why it's taking time. But the efforts are ongoing in the community, and we will keep you posted as to what happens on that front, right? Yeah, and I would like to acknowledge Masahiko Sawada. He's my colleague from Tokyo. He couldn't come here due to logistical reasons. So he's he's the one who's been working on this. And Ashutosh Bapat, I don't know if he's here. He's another colleague of mine. He's also worked on this. And obviously a lot of advice and criticism on the PostgreSQL hackers mailing list, right? So yeah, thank you. Thanks for listening. On time. 45 minutes exactly. Exactly. Clock snapshot.
Any questions? I guess there were a lot of questions during the talk, so.
Yeah, exactly. Yeah. Okay, thanks a lot.
Okay.
Yeah.
The join, how it behaves.
So in this case, you cannot optimize this join, right? So what will happen is, if there is a where clause that is part of that join, we will try to push that down to each of the remote nodes so that you get the least number of data. And then locally, you will have to perform the join.
So anyhow, you have to bring the data from both the servers and do the operation.
Obviously, there is no, see, you have to give the return answer back to the user. And in this case, you cannot optimize it. So you will do it by bringing data locally.
Okay.